Hello, in this video, we will just carry on with the limits at infinity. Yep. We will try to calculate a certain limits at infinity of a certain functions. Okay, let's start. We have example number 11. Limit at infinity of ratio of these two functions, cube root of 8x to the power of 6 plus 5 over quadratic function 4x squared plus 1. Computing limits at infinity, we're focusing on the leading terms only. That means this is the leading term and this is the leading term. Let me simplify, and I will just put cube root of 8x to the 6 4x squared. Because we learned that algebraically the other terms will disappear. They are not significant at infinity. This limit is x is approaching positive infinity, that we don't have to be worried for some simplification of the even roots. We have cube root. Okay, as soon as we have x, we always have to write a limit notation. Cube root of 8 is 2. Cube root of x to the power of 6 is x to the power of 6 over 3, which will be squared. Yeah, we will divide because it's cube root means rational exponent 1/3. Okay, and 4x squared. The same leading function, they will be cancelled out, ratio of the leading coefficients. This limit is 1/2. And if we will draw this function, this whole rational function, I mean ratio of these two functions, 1/2 horizontal line will be a horizontal asymptote for this function. Horizontal asymptote. Okay, another one, the same thing, limit at positive infinity, yeah, and behavior and leading terms. Let's see what we will have here. X approaches infinity. Fifth root of 32. Actually, I can rewrite like this. Fifth root of x to the power of 5, 8x. Limit as x approaching positive infinity. Fifth root of 32, I think it's 2. 2 times 2 times 2 times 2 times 2 is 32. Fifth root of x to the power of 5 is x, no problem. And this is odd root. We will have no problem with the positive or negative. And the same leading function, xx, they will be cancelled out. 1/4 the ratio of the leading coefficients. Okay, now we have to be careful because x is approaching negative infinity and we're dealing with even root. Square root of 16x squared and 2x, they are the leading functions. Let's see what ratio is telling us. Square root of 16, square root of x squared, and 2x. This one is no change. Limit x approaches negative infinity, 4, and now square root of x squared can be cancelled out, simplified x, but we know that x is negative. We will make it positive times. Okay, then negative 4x divided by 2x, negative 2, because the main function is the same, x, the same function, and then the ratio of the leading coefficients. 4/2 with that extra negative, which we get from the simplifying even root at negative numbers. Okay, -2 is the final answer. And of course, this is a horizontal asymptote also. Okay, another one, negative infinity and even root. We have to be careful, but also we have to always add arithmetic. And yeah, we are not allowed to assume that the answer will be like negative right away because x is approaching negative infinity. We know that. Okay, leading term, square root of 9x to the power of 6, and then x cube. That's the leading. Square root of 9, square root of x to the power of 6, x cube. Let's simplify. Limit as x approaches negative infinity. This is x cubed, no change. This is 3. Square root of 9, it's 3. And now square root of x to the power of 6 will be x to the power of 6, and that 6 will be divided by 2, 1/2 x, x to the power of 3 cube, yeah. because square root means power of 1/2. 6 times 1/2, it's 3. But this is negative values. That means theoretically, I will put negative. Okay, I have to put negative because that number is negative. And if I will keep without the negative, I will create negative number, yes? With that extra minus, x itself is negative. We cannot, we remember like square root of -5 squared. It's not -5, it's +5. But if I will copy -5, I have to put minus +5. We did this during the class, okay? And now when we simplify, I might rewrite this a little bit more clear. Negative x to the power of 3 is -1, and then x cubed, because negative to the power of 3 is still negative. I mean, I can write like this, a little bit clear, because negative will stay, x cubed, of course, will stay. Leading functions are the same, they are cancel out, just the leading coefficient, -3. Please, yeah, be careful. Okay, another one, also x is approaching -infinity, and even root. Because if it's odd root, then we don't have to be worried. We're not putting any negatives. Okay, this is leading function, and this is the leading function. Let's just copy square root of 16 and square root of x to the power of 4, 8x squared. This one is interesting. Of course, I will follow all of the steps, all of the simplification of the square root expression, but we may notice just kind of like mathematically common sense. We have x to the power of 4 and we have x to the power of 2. Everything is even, the powers are even, and x is approaching -infinity. I believe the final answer, whatever the ratio of the coefficient or whatever the number will be, must be positive, because it's x to the power of 4, x to the power of 2, which these even powers makes the answer positive. But let's see how we can get this. Square root of 16, this one is not a problem. We have to rewrite like just copy. Square root of 16 is 4. And now square root of x to the power of 4 will be x squared, right? X squared. But just to follow this, that x, we have to make it positive, because that x itself, it's negative, because x is approaching -infinity. We know that doesn't really matter if we miss that negative, because we squaring anyway, that outer power end up being even, which will make positive. But just to be precise, yeah, if this negative will be missing, let's pretend on the written homework assignments, yeah, I will put negative and I will say that's a little bit tiny mistake. But we know where this comes from, because x itself is negative and we making positive. Okay, but everything is positive, as we said. -x squared, I can rewrite this. It will become positive x squared. Even if it's -infinity, the answer is x squared is cancelled out, 4/8, 1/2. Right, that's interesting. That's interesting. Even if x is approaching -infinity, the answer is positive. Okay, and another thing, 16, -infinity. Let's speed it up. We will have square root of 4, because this is the leading and this is the leading. It's 2. Square root of x to the power of 6 will be x to the power of 3, but negative, because x is approaching -infinity. This one stays without the, okay, -1/2 is the final answer, because the negative will stay. -x cubed is -1 times x cubed. X cubed is cancelled out, -2/4, -1/2. Okay, good practice. Another list. Okay, now a little bit different. Limits at infinity, still limits at infinity, and a little bit of trigonometric functions. Of course, we assuming, because this is calculus class, and we assuming that all students know how functions sine and cosine behaves. Yeah, the sinusoidal model. We went through the chapter 1. I mean, I can just get the graph. Yeah, that's we know this answer. This actually, especially number 17, it's the precalculus. Function sine for the period between 0 and 2 pi, 2 pi looks like this, but we know that this periodic function is going on and on. Maximum value is 1, minimum value is -1. Yeah, it's happening here and it's happening here and so on. We also have this direction. Okay, this is sine of x. Okay, so now limit as x is getting bigger and bigger in the positive direction, how function sine of x behaves. Oscillate, right? Like 1, -1, 1, -1. It doesn't really like approach one finite direction. This limit simply does not exist. We may think plus or minus 1, but we're not really writing this. Yeah, this limit does not exist. We know that the limits sometimes are not defined. Okay, now limit of the sine over 1 over x. Okay, interesting, a little bit different. Yeah, the graph will look a little bit different. But what we can do, since this is definitely sine function is a continuous function. We may, and x in this case is just placed in the inner function. We may, yes, we have this theorem, we remember from the basic laws of limits, we may just focus on the limit of the inner function first, and then apply the outer function, which is sine. Okay, limit as x goes to infinity of that quantity, 1 over x. 1 over big number is a small number. It means limit inside is 0, sine at 0 is 0. Done? That's cute limit. Okay, 19 is a little bit challenge, but we might try to do it. First of all, what we see x times sine of 1 over x. We know that this limit we just did, number 18, is 0. It means this limit is 0. And we end up with indeterminate form infinity times 0. Yeah. I mean, this one is maybe more appropriate for the further sections 4.5, but let's try to use some tools. Let's rewrite, simplify, manipulate the numbers, use the algebra skills, precalculus, and some section from our chapter 2, and let's get the solution. Let's try to rewrite. What we can do, in case, we may remember for the future sections, in case of indeterminate form, the product form, infinity times 0, we may switch this for the quotient. I mean, I will keep function sine of 1 over x on the top, and I will flip that x. Instead of multiplying by x, I divide it by 1 over x. Simple, right? Simple. Okay, now I will probably, some of you see the answer right away. Okay, I can say really fast. Oh no, let's make more labels. Now, I have similar situation. I have an inner function. I have 1 over x, and I have to focus on this limit. But what I will do, that 1 over x, I can maybe call t. Okay, let's say t. I mean, we will rewrite this as a sine of t over t. Since I have t, I would like to know what t does. And t, t is defined, let's check here, t is defined as a function 1 over x, however 1 over x with the behavior at infinity. That means it's a limit, it's the behavior at infinity, because we can see we have to evaluate this. We can kind of do together, but let's just do this way. That means my t value is the function 1 over x, of course, and we have to respect the limit. How function 1 over x behaves at infinity. 1 over big number is a small number. So actually, t is approaching 0. That's the 0. Yeah, because 1 over x, 0. 1 over big, 0. And now I hope we remember this limit. I think it's section 2.6 maybe from chapter, yes, from chapter 2. Sine of 0 over 0. We prove it, we know what it is. The limit is 1. Beautifully, we use some algebra trick and property from this chapter. Excellent. Okay, another set of limits at infinity. This is just, yeah, I think we mentioned this, that we may have limits at infinity, which are infinite limits. Saying this, that when we computing a limits at infinity, x approaches infinity, function also goes to the infinity. Yeah. Remember rational function, like for instance, I can give you an example as x goes to the infinity, maybe 3x to the power of 4, x squared plus 1 over x cubed minus 5. We focus on the leading term, x to the power of 4 over x cubed, we will end up with x. That means numerator is winning, x goes to the positive infinity, the final answer is positive infinity. Yeah, because numerator is winning. We have to respect arithmetic. If this will be -3, for instance, then the answer will be negative infinity, even if x goes to the positive infinity. Of course, basic arithmetic. Okay, and then I think, okay, I have that list. Okay, let's see. Which actually, yeah, we talked about this, knowing the graph of x cubed, how x cubed behaves at infinity. We will cube the big positive numbers and we will get infinity. We did this. Negative infinity cube, if we will cube big numbers, we will get negative infinity. Okay, 22 and 23, we have to be careful, because if we think about it individual, we have a difference of two functions, and thinking individually, x squared and x, both of them goes to the infinity as x goes to the infinity. This means we are facing another indeterminate form, the difference. We know infinity minus infinity could be anything. We have to focus like what kind of infinity, what kind of expression is hidden behind these infinities. Okay, yeah, let's use some algebra steps. I will factor out the leading term because we know that trick. We have to be more clear. If I will factor x squared, then I will have 1 minus x over x squared, because then we simplifying, we will get the same. Limit as x goes to the infinity, this is x squared times 1 minus 1 over x. Okay, 1 over x goes to 0, no problem. At infinity, of course, at infinity. Okay, so we end up with x squared is infinity times 1. Infinity times 1 is not indeterminate, it's simply infinity. Okay, we managed to remove algebraically the indeterminate form and get just the product of two terms which are not indeterminate. They are actually defined. Infinity times 1 is just infinity, okay? Okay, another one, similar, and we will probably use this. Okay, this is square root of x squared plus x, everything is infinity minus x, because the square root ends here. Another difference, the indeterminate difference form. Yeah, they are still good for section 4.5. If you will check our calculus textbook, the 4th edition of calculus by Rogawski, John Rogawski. Okay, shall we do the same thing? Let's try. First of all, let's factor out x squared under the square root. This means we will have 1 plus x over x squared, still everything under the square root. Okay, let's simplify a little bit. Now I can rewrite as a square root of x squared and square root of 1 plus 1 over x when I simplify this, minus x. And now square root of x squared, everything is positive. I can rewrite as a x and then 1 plus 1 over x minus x. Okay. Okay, actually, let me go because you know how I like to align the equal signs. Now, x and x is a common factor. Let's factor out. We will get this minus 1. But what we have, this is infinity, okay? Because x goes to the infinity. 1 over x goes to 0. 1, square root of 1 is 1. 1 minus 1, actually, this is 0. Oh, no, wait, I just like to indicate everything clearly for my students. Infinity times 0, it's also indeterminate form. That means I did lots of work. However, I end up with different indeterminate form. What we can do, we have to simplify, and we can, yes, again, I can use just algebra, and I will try to use just algebra because in section 4.5, we will learn another magic tool, which I can't use it anymore, but we have a tool. We still have a tool, algebra. We probably remember when we have some issues or some indeterminate forms with the expression which involves square root and especially expanded form, we may use multiplication and division of the conjugate expression. Yeah? Always the square root and the conjugate expressions are helpful. And that's what I will do. Okay, I will solve them on the other side, which actually we know. I can rewrite this. That means I will do x 1 plus, now I have to keep everything. And as I said, I will multiply and divide by the conjugate. 1 plus 1 over x plus 1, because that was minus 1. And yeah, that's the multiplication. And of course, I have to divide. Because when I multiply and divide, we can see I can still cancel out that blue expression, but I will not. I will multiply the conjugate. Let me add a slide and we will. I will add a duplicate slide. Oh no. Okay, I can add a duplicate slide. Actually, no, I don't. Oh, no. No, don't worry. I have this, and then I have room for the other one. Now we're ready. Okay, let's see. Okay, that's our work. Okay, maybe I can copy. Oh, no, let's on the next slide, which is the blank slide, the room for the solution. When we multiply the conjugate, I can maybe write on this one, like when we have a minus b and a plus b, like a, the first quantity, b, the second quantity. We can see our square root is a, 1 is b. When we fold everything, we will have just a squared, b squared, and minus. And that means I will use this one. When we square the square root, everything is positive, then we will end up with just 1 plus 1 over x and minus squaring b, squaring 1, minus 1. Okay. You remember what we had? Limit x is approaching infinity, and we will have x. This was 1 plus x plus 1. And we squaring the first quantity, squaring the second quantity, and minus. It's always helpful remembering about the conjugate. Okay, now this is gone. 1 minus 1, 1 over x. Do you think we are close to the answer? And x times 1 over x, we're getting 1 on the top, and we still have this expression. And limit of 1 will be 1, constant. 1 over x goes to 0, then we will have square root of 1 plus 1. The final answer is 1/2. Interesting. Infinity minus infinity, and we getting 1/2. Really nice example. We may do maybe a little bit faster with some calculus tool, but we don't have to. We are strong with pre-calculus and we can still solve it. Okay, and then I think, okay, that was, let me just put, this was infinity, this was negative infinity. I think this was infinity, this is 1/2. Was this infinity? Yes, because it was infinity times 1. Okay, and now we have just 24, 25, 26, almost nothing to do because we just need to state the end behavior, limits at infinity. That's the end behavior of function e to the x, e to the negative x, ln of x. We know how they look like from pre-calculus. And they are quite important models. E to the x is the exponential function and looks like this. 1. We know that as x is getting bigger and bigger, e to the x will be even bigger, infinity, big infinity, really fast. Now the other way, e to the negative x, it will be the inverse, because when we put negative in front of the x, the mirror image with respect to y. And as x is getting, we may say 1 over e to the x, like algebraically, if we like this, and e to the x at infinity goes to infinity, 1 over infinity, 0. But we can also see, as x is getting bigger and bigger, the graph is approaching 0. Of course, horizontal asymptote. If the limit is infinity, then there's no horizontal asymptote. We can see this. And natural log of x, it's the inverse function to the first one, looks like this. Okay, as x is getting bigger, the values are also getting higher and higher, really slowly. It's increasing really slowly, but it's approaching infinity. But that's pre-calculus. Okay, and I think, let me check, we did this one. We did this one together. Okay, I also have the set of those. Okay, let's try. Yeah. You may pause the video, you may go and have a glass of hot tea or coffee and then come back, okay? But don't miss any questions. Let me do it. Okay, we have 1, 2, 3, and 4. X is approaching 1. Okay, that's a little bit different. No, that's not infinity. But okay, let's do it. Or shall we just do the infinity? Because they look like indeterminate forms. Okay, since I said, let's do it. This will be just we can see there are not really limits at infinity. Number 3 is the limit at infinity. Let's actually start with this one, just to be fair to the topic, and then we can solve the other one as a review of the limits. Okay, number 3, we know that we can just focus on the inner function. Sign will stay as an outer function, pi over x, as x is big. Pi over big number is also a small number, 0. Sign at 0 is 0. We did similar. Okay, done. Number 3 is done. Okay, number 1, I'm afraid, is the indeterminate form. Square root of x minus 1. X is approaching 1. 1 minus 1, of course, from the right-hand side, everything is positive, 0. And then 1 minus 1 in the denominator, it's 0. 1 over small number. 1 over small number is a big number. Big number is infinity. That means this expression is infinity. How function sign behaves at infinity is undefined, D and E. Okay, so this one is, that limit is undefined. This one is not necessarily like 0 times infinity, like we usually state the indeterminate form, but infinity is also like non-existence, like limit doesn't exist as a finite number. That means 0 times, that's times, not difference. Something that is undefined is also indeterminate form. Okay, if you remember what I did for the previous x times sine of 1 over x, I will do the same. Yeah? This is product form. I will change for the quotient. I will keep sine function, and I will keep the reciprocal of this, because dividing by fraction means multiplying by the reciprocal. That means when I change this, I will get the same expression as the original. And what we do have, let's try limit as x goes to 1. I will use my algebra. I can rewrite this to the power of 1/2. I think it makes sense. However, no. Do you know what we can do? Because this will be, we can still do it, but I don't want to be so. Okay, let me change something. The same concept. I'm just trying to, let's wait a second, 1 second. Okay. Yeah, I was actually thinking that we might change the function for to be a little bit easier, but I think that's the wrong way. Okay, because we also, you see how the process looks like. You can always make some steps and they could be wrong, but it's the good thing is that we have a knowledge and we can figure out what's the good theorem. I forgot about one theorem, and let's apply. Do we remember the squeeze theorem? I think it will be great in this case. Okay, we do have a function sine of that angle. Yeah, because we call that's the angle. Sine, yeah, function is always squeezed between -1 and 1, sine of any angle. We may shift the function, do the transformation, but no, sine of any angle. Okay, now I can multiply each of this part. -1 times the square root of x minus 1 is negative square root. This will be times 1, positive square root, and square root of x minus 1 times the function sine of 1 over x minus 1. And now, as x is approaching 1 from the right-hand side, this will be 1 minus 1, 0. This limit is 0. We not consider -0. As x goes to 1 from the right-hand side, as x goes to 1 from the right-hand side for this one, it's also 0, 1 minus 1. And if both of the limits are 0, the upper and the lower function, the middle one is forced to be 0. So we don't have to do anything. This limit is 0. Based on the squeeze theorem. Okay, interesting. But I was misled by the other example. Okay, perfect, because this one I was trying to do this way. No, this limit is 0. As we can see, we're not allowed to say right away. Yeah, we have to have a good reasoning. Okay, let's see the next one. X is approaching pi over 2, and we have x times cosine of x. Let's do the direct substitution. Pi over 2 and cosine of pi over 2. Pi over 2, cosine at 90 is 0. 0 times a finite number, that's 0. We have no issue here. This limit is 0. This limit is 0, we just did. And I don't even want to think. I believe, we have to use the squeeze. We have options. We can just algebraically manipulate, or we can use the squeeze theorem. But let's say square root of x at 0 is 0. And then we have pi over x. Yeah, pi over x pi over small number is a big number. Sign at big, at infinity is undefined. +1 is undefined. Okay, that's mean again, similar thing, D and E. Yeah. Let's use the squeeze theorem and let's finish the session. Okay, shall we do the squeeze theorem? I can try sine function, but let's see if this will work. Sine function of pi over x, let's do first this. Sine of any angle, it's squeezed between 1 and -1. When we square, when I square the values, the maximum value will stay 1, squared is 1, but squaring, we always get positive number. Please do not be misled, because sine of square is just the function above the x-axis. That means it's just positive. Okay, everything becomes positive, but still not greater than 1. Now, when I add 1, because I have to create my function, when I add 1, 0 plus 1 is 1. Sine square pi over x plus 1, and 1 plus 1 is 2. Okay, I added 1. Yes, I added this. And now let's multiply by square root of x. Square root of x times 1, square root of x times the function of this, and 2 times square root of x. Now, interesting, we have square root of x and 2 square root of x. As x goes to 0, square root of x goes to 0. We know the graph. 2 times square root of x also goes to 0. Yes, the squeeze theorem works, because if both of the functions that we squeezing our middle function, the original function, if the limits are the same, this limit is forced to be the same. Okay, this is 0, but it's really important by the squeeze theorem. Okay, we cannot say otherwise. We don't know. If I will have not enough information, sometimes you can say it's not enough information. Yeah? Okay, let's finish. Yeah, let's finish our session with this. And just the number 1. I think I started using some algebra, which I forgot about the squeeze theorem. Okay, enjoy the limits, mainly at infinity, and the last slide. Thank you.